All right, welcome back to Differential Equations here. So we're going to cover the first section in chapter 2, and you might be asking yourself, are we going to learn how to solve these things yet? Nope, not yet. So we're going to talk to you about some graphical methods, and these are important, and some other ways of kind of looking at it, because quite truthfully, I mean, this entire class is based off of a lie. um, Differential equations, like real ones, like you're going to find in the field, there is no solving them. Okay, there's approximating them. There's graphically dealing with them. So all of these little techniques that we show you at the beginning are kind of ways for you to kind of approximate or kind of jump at an answer without you actually having to solve it, because most of them you can't. So yeah, this entire thing, this is all a lie. We're trying to tell you that you can solve them when, in fact, you probably never will be. But that is not to say that in your mechanics class, you're going to be confronted with these things and they're going to expect you to be solving them. So you're going to have to learn the techniques, okay? Electrical engineering uses this stuff all the time. So just because you can't solve, you probably won't be able to solve a differential equation you find in the wild, doesn't mean that the whole class is useless, because the techniques that you're going to learn can give you some insight as to what's going on. And the techniques that you're learning in the early chapters are like, I never really needed that stuff. I'm like, yeah, I got news for you. That's sometimes that's the only thing you got. So, here we go. And again, we lie to you because, the textbooks show you nice pictures of differential equations that you can solve. And he's like, why would I need to do all these methods for that? I'm like, because that's what we train you on. Okay, you can learn all the fancy harder stuff as you go along, and you can just start adding more and more complexity. But for the first class in DE, let's stick with the first class in DE. Okay. So the first thing we're going to talk about for this section is something called a slope field. Okay, and this is something that is actually quite useful. And we might even solve a few, lovely. You might even be able to solve a few, or at least approximate the solutions to a few of these, even though we may never be able to solve them analytically. You may never learn a technique to solve this thing. But let me give you an example, and we can kind of start working through this thing. So I'll give you a dy by dx, okay, is equal to 3x minus 2y. Okay, so first order linear differential equation. Okay, and we want to graph the slopes, right, on a coordinate system. We'll say x goes from -5 to +5, and y will do the same. Okay, so kind of like you're scaling your calculator window, right? You're going to have a little grid, 10 by 10, right? 5 to -5. It's 10 points in between them. -5 to +5, 10 points in between them. 4, 5. 1, 2, 3, 4, 5. Okay. 3, 4, 5. All right. And you might be tempted, and this is certainly a very natural way to approach this problem, and it's not a terrible thing to do. So you might say, well, let's set x equals 0 and y equals 0. So we'll have dy by dx is equal to 3 times 0 minus 2 times 0 is equal to 0. Great. So we have, and we'll do it in red. So I've got a little slope here that's 0. Okay. And the next one, let's go ahead and set x equal to 1 and y is equal to 0. And dy by dx is going to be 3 times 1 minus 2 times 0, which is going to be 3 minus 0, which is 3. And we have to remember, this is a slope, okay? So what you're going to do is you're going to draw a little line segment here, and you're going to try to approximate a slope of 3. There, okay? Neither of us, nobody is here is trying to be an exact, like, well, that doesn't look like a slope of 3. That's actually a slope of As long as it's bigger than 0, it's bigger than 1, it's bigger than 2, and it's maybe less than 4, good enough. Okay, we're not trying to, I know the book will say, like, use a computer software program to get an exact, like, no, we're not doing that. And you can go on to do this, right? And you've only got -5 to +5, right, in both directions. So that's only a 10 by 10 grid, and you only have 100 arithmetic problems to work through. But we live in the 21st century, and this is how you would set a computer up to solve this problem. And so this is a very natural way to think, because we have taught you guys to, like, think how a computer would solve the problem and then run that algorithm like a human slave. Okay. But no, you're going to make the computer do this, and it's going to draw little line segments all over the place, and you're going to end up with a nice little slope field for it. Okay. And that's great. That's exactly what we want you to do. Okay. I don't really want you to do it that way. I want you to be a little bit more clever about it. Okay. So let's go ahead and let's just redraw this for a moment. Okay, we've got dy by dx, and that was equal to, what did I say? We had 3x minus 2y. There we go. And what I want you to do is say, instead of setting the x's and y's, we're going to say 3x minus 2y is equal to dy by dx, and we're going to set dy by dx equal to 0. So we have 3x minus 2y is equal to 0. We have, right, 2y is equal to 3x. We'll just swap the sides there and say y is equal to 3/2 x. You guys can graph 3/2 x, right? What did that graph look like? I should have picked easier numbers, because now I got to just graph, right? We have to graph y is equal to 3/2 x, which is something like this. Actually, I'll tell you what we're going to do. I'm going to see it. I can't just erase everything, can I? No. All right. So what I'm going to try to do is draw this in real light. Okay, so let me pick a nice light color. So I know this is terrible, right? So I'm going to pick a nice light color in, something like that. Okay. We'll say this is y is equal to 3/2 x. But what was the slope for that? Well, the slope for that was dy by dx was equal to 0. So what I'm going to do is I'm going to draw my little line segments to be 0 slope here. Okay. So, but you're not going on the points that we were supposed to go on. Like, yeah, I know. This is sloppy. Okay. But look how many, if I really wanted to just go through the points, I mean, look how many I've got and how much work it took. So we don't want to do all of that. So yeah, I definitely should have been more clever in picking a problem here. Okay. Because the next thing is like, well, let's set dy by dx is equal to 1, right? So that's not so bad. 3x minus 2y is equal to 1. So let's go ahead and swap. We've got 3x, right, minus 1 is equal to 2y. 2y equals 3x minus 1. So y is equal to 3/2 minus 1/2, 3/2 x minus 1/2. So all we are doing here is we're coming up with, right, same thing here. I'm going to extend my 1/2 a bit here. Okay, to do this. And this is, right, the line is the slope, y equals 3/2 x minus 1. So when I go ahead and draw in my slopes, these, by the way, this line here, this line, and this line, these are called isoclines. Nobody will ever ask you that. But what I'm trying to do is draw a slope that is less than the slope of the line, but I'm trying to approximate a slope of 1 here. Okay, pretend that these, right, are less steep than the line, but more steep than this. Okay. What happens when we try to do, say, -1? Okay. So what if we do this? We say 3x minus 2y is equal to -1. And we could say this is 3x plus 1 is equal to 2y, or y is equal to 3/2 x plus 1/2. So we're going to go up here. Again, I'm going to use my light gray here. to see if I can't sketch out a line. And I will do this here, right? And then in red, when I'm drawing my little line segments, okay, we're going to go ahead and draw. I don't want to make them too steep, but these are all supposed to be slopes of -1, okay? And we're going to continue in this way where the next line, right, the next line down here is going to have a slope of 2, right? Or I'm sorry, yeah, it's going to be a slope of 2 because we're going to set dy by dx equal to 2. And then we're going to set dy by dx equal to -2 up here. Okay, so let me draw some of this in so we could just, here we can do this. And along this isocline, along this line here, we're going to have dy by dx is equal to -2. All right. I mean, can you see that with how that's coming along, that we're going to set dy by dx equal to, instead of -1, we're going to say -2. And then this is just going to be a little bit steeper. Okay, pretend these are steeper than these. Okay, and I suck at drawing all of these little lines here. But, you know, and then gray. And then we set dy by dx equals to +2. So we're going to get the next one down here. So this was, oh, that was a terrible line. Okay, so, oops, wrong one. I went light, not noticeable gray. Okay, so this one's going to be a isocline with you know, y is equal to 3x minus 2. And that was a positive slope of 2, which is going to be really hard because it's got to be steeper than this, because this line is only, right, 3/2. And then what we're going to do is we're just going to dot in into this mess. Okay, I'm sorry. You guys are going to have much neater graphs than I am. But we're going to go ahead and go ahead and, right, it's going to be really steep, less steep, and then it's going to come to zeros. And then we're going to go up, 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 and up. Okay, and that's going to be how we graph this stuff. All right. So that is a much easier way to go through and make a slope field without doing it the way a computer would do it. Because I really, you know, this is a good thought, is to go through a matrix like this, right? You could do like I guess you could do like a nested for loop or something, do the x's and do the y's, and write this thing out in Python, or write this thing out. Well, we'll show you how to do it in Octave in a little bit. I'm kind of waiting to 2.4 because that's where we do the numerical stuff. But we could do all of that with something like this, okay? And but I would rather you approximated it and make kind of a messy drawing this way, because it's more organic, but we don't need to mess with the computer just yet. I want you to have a feel for, like, what am I supposed to be doing with this? Okay, let's do one more, maybe a slightly nicer problem. Okay, not really, but this one has something to watch out for. So let me go ahead and make sure I get to that example here. Okay, so let's look at what if we had, like, y tick was equal to x over y? Like, uh-oh. Well, again, you know, we will be able to solve the time we just did, right? That's coming up. But this is just y prime equals x, right? So this is y dy by dx equals x. So y dy equals x dx, and that's like almost a Calc 1 problem, right? That's not a big deal. So this is the solution curve we're going to get. Is not going to be a great mystery to anybody. Okay, but let's go ahead and do solution curve with this, or slope field with this. So these have a lot of different synonyms, right? I mean, I've been calling them slope fields for the longest time. I guess you can call them direction fields. I think that's what your book calls them, as a direction field. But there's a lot of different words that are used to describe this graph. Okay, so again, in the same method, right? We're going to say set y equal to x, or set, sorry, we'll keep it as y prime. Easier that way. Okay, and then what if, we'll just set y prime equal to 0. So we have x over y is equal to 0. Well, that's only going to happen when the top is 0, right? It's a rational function. So the only way it's going to be 0 is if x is 0. So if I go over here and make a little coordinate graph here, right? Where is the line x equals 0, right? That's a line, right? X equals 0. That's a line. That's this one, right? X equals 0 is this line right here. And what did I say my slope was here? My slope was 0. So we're just going to type in little slopes here, right, on the line x equals 0. Right? And then we can go through and do a whole bunch of different things. We could set, how about it's equal to 1? Right? We could say x over y is equal to y prime, which is equal to 1, because we're setting y prime equal to 1. So that's just the graph, right? That's x equals y. That's y equals x. So when I go to draw in my isocline here, right, it's all the slopes are the same on this line. This is going to be a little bit hard to see because the slope of the line y equals x, the slope is 1, and we're trying to graph slopes of 1. So it's going to overlap a little bit here, but we'll go through and do this. Right, and similarly, we can go with, right, what if dy by dx was equal to -1? Right, we could say x over y is equal to -1. Set y prime equal to -1. So now we have, right, y is equal to -x. So again, that isocline is going to be kind of weird because the slope of the isocline is also the slope that we're trying to deal with. Okay, pretend those are straight. All right, so I have my slopes here. All right, what about 2? Right, what if we just change this a little bit? All right, and make, what was this? This is x over y is equal to y prime, which is equal to 2. Then I've got x is equal to 2y, or y is equal to half x. So that's a little bit easier to start dealing with because we've got, here's half x. Right, but on this isocline, my little slope fields pieces here, right, that's, they're something like this because they're slope 2's now. Okay, that's pretty steep for 2, but you know what I'm saying. Okay, and then the same thing, right? Check the -1. So we'd have slope, right? If we change this guy here to a -2, then we're going to have y is equal to -half x. All right, so we can go through and do that. Okay, so I'm trying to do something like that. That's y is equal to -1/2 x as a line. That's my isocline. And then what we're going to do is we're going to draw in, and we've got negative values here. All right, and we could keep going with 3's, right? And that would even be less steep here, but we would have a steeper, as the slope segments would be steeper. Okay. So as long as we remember, right, and then up here, right, they're going to be, right, if I plugged it in and I said, instead of going with this kind of a number, we could do a fraction. So I could say set y prime equal to 1/2. So we have x over y is equal to y prime, which is equal to 1/2. And at that point, we get y is equal to 2x. So there's my isocline is y, the graph y equals 2x. Okay. So I know that that's not really much of a challenge for you guys. Y is equal to 2x. And what was the slope on that isocline, right? It was 1/2. So when I go to plug this in, right, then we have 1/2. So not here, but we're going to be doing something like like that, right? Because the slope is, I don't want to draw, it's a little steep, okay? Not as steep as 1, but, the slope here is a half. So when we go to draw this whole thing in here, okay, see, this one's not so bad, right? But, well, so as we get closer and closer and closer, right, and it's going to get steeper until it actually like levels out, and then it'll do something like that. Same thing in this direction, okay? That here we're kind of running into this, and we're going to get something like that, depending on where you start, okay? Depending on where you start. But that's how we're going to end up something. Okay, so that's our. I'm just trying to. It's a terrible graph. All right, let's see. So I want to do this. It's gonna be flat here, and we're gonna do something like that. But as we get further and further away, this is gonna do. Right, it's gonna get a little bit bigger. Okay, same thing over here. Okay. We want to kind of approximate the pieces you can as you're coming in. Take the easy ones and then do it that way. All right, I know that was awful. A computer really would do a much better job, but I don't want to quite go into hitting with you with Octave just yet. This is the first week technically, so here we are. All right, give me a moment. I think I got to put away a vocal kitty here. All right, hopefully that fixes something. Okay, someday I'll show it to you guys. All right. So, next idea, all right, is something called autonomous curves. Okay, this is another graphical technique, and it is used when the independent variable does not make an appearance in the differential equation. So, something like dA by dt equals A. This is something called autonomous. I can't spell autonomous. Autonomous equations. Okay. Autonomous equation. If there was like a minus t in here, then it would be a non-autonomous equation. Okay. But we're just talking about right when we only have the dependent variable in the equation. Okay. I think the most common example is something like dy by dt is equal to k times y, and then like an a minus y. Kind of like a zombie outbreak on a cruise ship or something, okay? And this is actually very common for diseases as well, okay? So what we're going to do is we're going to do what they call a phase diagram, okay? And it's a one-dimensional graph, okay? It's a one-dimensional graph. And what they want you to do is come up with what they call the critical points, right? You remember from Calc 1, critical points are where dy by dt equals 0, okay? So what would y have to be for dy by dt to be 0? And that would be at y equals 0, right? And it would also be at y equals a, all right? These are the spots where dy by dA would be 0. Okay, so I'm going to go ahead and use a different color here because I want to sketch in the actual graph. Okay, so phase equation, it's just a one-dimensional graph, kind of like we're on a number line. So that's all we're really doing here. Okay, there's another graph. I think it's, what the heck is it called? Phase diagram. I usually call them both phase diagrams, but one actually has a different name. I didn't write it down. I should have. All right. Pick a point pick a point for y that is a little bit bigger than a, right? And you could always do this. You could say, well, let a equal 3. So if y is equal to, say, 4, right? 3 minus 4 would be a negative number. So we'd have 4 times something negative. So we'd have a negative value. So we would have, when y is a little bit bigger than a, right? Then we're going to have dy is going to be negative. Okay. Pick any point between 0 and a. Okay. What's going on in here? The only two zeros are going to be these two. So pick a point between these two zeros. All right. And if I do that, we could say that, right, if a is equal to 3, pick y is equal to 2. So we have 2, 3 minus 2 is 2. It's positive. So no matter what happens here, right, we're going to be, dy by dA is going to be going up. Okay, now remember, at y equals a, dy by dt is going to be 0. I keep using, I'm sorry, I was using a's in one example and y's in another, and I apologize. So y is between 0 and a, right? Dy by dt is going to be 0 at this constant. Okay, but between 0 and this constant, then dy by dt is going to be positive. And then pick a y equals a smaller number, right? Pick y equals -1, right? We have negative here, 3 minus -1, right? That would be 4. So we have negative times positive. That's going to be negative. Okay. Now, when we go to the other kind of phase diagram, y equals 0 is going to be what they call a repeller, because every point that's around, either above or below this thing, it gets pushed away from this line. And I'll bet you can figure out what y equals a is going to be called, right? That's going to be an attractor, because it's all the points that we pick are going to be attracted to this line, right? If you pick anything bigger than a, it's going to go down, it's going to hit his eventually. Any point here is going to hit this eventually. So this is going to be called an attractor. All right. Now for a two-dimensional phase diagram, all right, we can draw a graph. And let's go ahead and change my color too. Yep. So here's my y. Here's t. Okay. I know t doesn't make an appearance. So this is y equals 0. This is y equals a. So we're not really trying to show off and say where this is, but right at the points y equals a, then dA, right, or dy by dt was 0. So all the slopes here are going to be 0. All the slopes here are going to be 0. Okay. So do you remember what was happening, right? What happens when y was greater than a? Well, it was attracted to this line here. So if we start with t something like that, right, we're going to be kind of moving into this attractor, this y equals 0. Okay. And then what happens in here, right? Now, I don't know exactly what's going on here as far as like what the behavior is. It might do something like this, or it might just curve in like this. We don't know. Okay. But what we're going to see is no matter what t we start at, right, it's going to be pulled into this y equals a value. Okay. And then I don't know what the context of this problem is. Clearly, if y are people, we're not going to have negative people. But, you know, if we are talking about a situation where it could be negative, then anything we have is going to be pushed away from this y equals 0 line. Okay. Like we have right here, it's going to be pushed away from it. Okay. So this is a two-dimensional phase diagram. And then one-dimensional phase diagram. This is usually what they mean at this point in the chapters, but that is a way of dealing with autonomous solutions. So you can kind of graph them and see what's going on with stuff like that. Let's see. We did the critical points. I don't know if we really need to do another example with that. I think we're pretty good with this. There's a lot of hand wavy stuff. So that was a lot of 2.1, and it's again, it's like, am I going to solve these? I'm like, no, we're just going to draw the behavior of what we think is happening. Okay, this is like a training your intuition kind of a chapter at this point. All right, so I'm going to leave you with that, and then I'm going to meet you for 2.2. Maybe, just maybe, we'll solve one. Okay, so I'll see you in the next section.